Welcome. We are in Chapter 4, and today we look at 4.3, Graphing Functions. This is kind of an old school topic. Nowadays, with computers and graphing calculators, it's easy to plug a function into a computer and see exactly what the graph looks like. But let's put ourselves into the mind of someone 50 years ago, 100 years ago, who was given a function like this and had to figure out how does it behave? What does it look like? So we'll see how the tools of calculus give us insight into the behavior of functions and how they look graphically. So let's take that function. And I've given you the first derivative and the second derivative. And what can we learn from those derivatives that show us how to graph the function? The original function is going to give us information about asymptotes and x and y intercepts. When I take the first derivative gives us information about critical points, where the function is increasing and where the function is decreasing. Critical points are going to be where the first derivative is 0, or where the first derivative doesn't exist. And where my first derivative is positive, that's where the function is increasing. Where the first derivative is negative, that's where the function is decreasing. The second derivative tells me about inflection points and concavity. Inflection points are going to be where my second derivative is 0, or really where it changes concavity. The function is either concave up or concave down, and concave up occurs where the second derivative is positive, and concave down occurs where the second derivative is negative. So we can learn all kinds of graphical things about the function by looking at its original expression, the first derivative, and the second derivative. Let's turn our attention to the original function. How can I find asymptotes and intercepts? Well, factoring is our friend. Let's write this out in factored form. I can see there's an asymptote at -1 because the denominator is 0 when x equals -1. Now let's look at the numerator. When the numerator is 0, then the whole function is 0. Well, that numerator is 0 when x equals 0 and 3, and so that's where my x-intercepts are. And that's some good information that we got from our original function. Let's move on to the first derivative. Again, let me factor the top and the bottom. I don't claim that this factorization is immediately apparent, but with a little bit of work you could work it out. What do we know here? Well, how about our critical points? When the numerator is 0, that's when my first derivative is 0. There will be some critical points. So at CP, at x equals 1, x equals -3. And also the first derivative doesn't exist at x equals -1, where my denominator is equal to 0. So those are the points I need to test around in order to figure out where my function is increasing or decreasing. So let's make a little sign chart. I'll do that off to the right. I'll identify the critical points, so -3, +1, and -1 is also interest. At -3, the first derivative is 0. At 1, the first derivative is 0. At -1, the first derivative doesn't exist. I'll just make a little dashed line there. And let's start plugging in numbers around the -3, -1, and 1 to determine whether the first derivative is positive or negative. This is where the factored form of the first derivative will be most helpful to us. And I'll go through this quickly, but you can imagine if I plug in, let's say, a very low negative number, like -5, then in my numerator I'll have a negative times a negative, and the bottom is a positive, so that whole thing is positive. The sign of the first derivative can only change around critical points, so that's positive all the way throughout there. What if I throw in a -2 into that first derivative? Then I get a negative and a positive over positive, so that's negative. And how about if I put 0 into my first derivative? Negative, positive, positive. The whole thing is negative. And lastly, let's imagine I throw in a large positive number into the derivative, so I get positive, positive, positive. The whole thing is positive. So these are the signs of my first derivative, and that tells me that my original function f is increasing and then decreasing. It continues to decrease and then increases again. So I've determined increasing and decreasing for my original function. Let's turn our attention to the second derivative. Where is the second derivative equal to 0? Well, it's equal to 0 where the numerator is 0 and 8 is never 0. So in fact, there are no inflection points. The function has an asymptote at -1, so let's check to the left and the right of -1 and find out whether the function is concave up or concave down. So again, we'll make a little sign chart. Now this will be a sign chart for my second derivative, f double prime. And if I plug in a number greater than -1, I find that this value will be positive. Imagine putting 0 into the second derivative, for example. And if I put a very low negative number into f double prime, that value will be negative. So my original function f is concave down up until -1, and then concave up after -1. All right, at this point, let's try to actually graph the function. I'll make a little space here, and what can we do? So there are my axes. I'll put a -1, and there's some kind of asymptote there. The intercepts are 0 and 3, so there's 0, 1, 2, 3, 4. Those are the points where the graph intersects the x-axis. I look at my first derivative to know where the function is increasing or decreasing. Oh, there's a -3. So it's increasing until -3 and then decreasing after -3, but it hits the asymptote. Then decreasing and increasing, so it must decrease through the x-axis at 0, then increase at 3. And can I confirm this is concave down, concave up, and I have concave down and concave up. Yep. So looks good. So there is my very rough estimate, but not bad. An estimate of what the graph looks like using only the tools of calculus. All right, on the next slide, I have an actual picture of the function you've been waiting for. Here we go. And not bad. We can see at -3, there's the high point. The function goes increasing and then decreasing. It has an asymptote at -1. Goes through the origin, goes through +3. It was concave down in that region, concave up there. Hey, we did all right. Okay, so now for homework, look at the functions I give you, look at the original function, the first derivative, the second derivative, pull out all the information you can from those functions given symbolically, and see what kind of graphical conclusions you can draw. Go to it.